fluxes.
You don't need renormalization. I mean, this is a dramatically different theory. We are not talking about a new interpretation of quantum mechanics. We're talking about a whole new theory.
It's definitely not a new interpretation, because the fact that the waves move in reverse has very different physical consequences. That's an important point. I'm not just reinterpreting it. Just reinterpreting it wouldn't fix it. I think we have enough proof now that a reinterpretation would just change around the contradictions. It wouldn't fix it.
A new theory.
Yes. Now, the reason why I say no renormalization is needed, this gets a little bit into the philosophy, but physicists have gotten used to the idea that because quantum mechanical phenomena cannot be pictured in standard quantum mechanics, and things don't happen in a causal manner, physicists have gotten used to the idea that somehow theories have to follow from field equations or from the mathematics. So you start with the mathematics and somehow reproduce reality. But there again, I think we should go back to more the classical philosophy, which says that the building blocks are the real things. You discover the nature of the real things, and once you've discovered that, that explains the behavior. So what I would say is, we've discovered that reality consists of these fluxes. They move in reverse, and they obey what amount to renormalized Feynman rules.
Can your theory explain the Lamb shift?
I'm sure it would, yes.
Sure it would. Have you tried?
I have not gotten that far. I will have to.
That's what started all.
But you see,
that's what started
there again.
The Lamb shift is what started it.
There again, this theory allows you to explain things like that without, in that case, the use of a vacuum, which really isn't a vacuum, and so forth. Here, the waves that would be involved in those any of those stranger effects or renormalization effects are around all the time as real fluxes, and they do have some effects, and including things like so-called vacuum polarization. But now you can explain it in terms of real objects and not.
Everybody admits there's lots of flaky things in quantum mechanics. Okay, but the thing that drove us here was the Lamb experiment in 1948. Trying to explain that. That required a second quantization of the background field, and that explains it. They say it's the best theory we've got because it explains. Now, if you can't explain that experiment,
well, I'm sure this theory would, because again, it reproduces all the Feynman diagrams, including the ones that are relevant to explaining the phase shift.
The diagrams are based on perturbation theory. The Lamb shift requires second quantization. You must, if you can do a theory without second quantization, not quantizing the background field, that is a dramatic change.
Well, maybe the way to convince you that no second quantization is involved is to look at quantum statistics for a minute, where you think you would need operators and Fock space and all that. Would it convince you if I could show you how you deduce Fermi-Dirac statistics without?
The Lamb shift that I'm at.
Well, I can't do that for you today. I'm sorry. I'm not prepared to do that today. Very briefly, the way you'd account for quantum statistics. Let's see. I need slide 12. That's back a few slides. I'm sorry. That's the one. I'm sorry. That one. As I indicated before, when a particle travels along its wave, it emits various other waves, or establishes mutual coherence with them. Now, one of the diagrams involved would be a diagram that involves very soft photon waves. Now, if you have a very, very soft photon wave, this re-emitted wave, in effect, is going to be the same wave. Only if it's a fermion, it's going to be out of phase with the one that's already there, because the vertex, standard quantum electrodynamics, has a minus sign, so you get an out-of-phase re-emitted wave. So if you can imagine this particle being in a stationary state of some kind, there has to be a wave there to begin with. No particle can go into a state unless there's a wave there to stimulate it into the state. But once one particle is put in, it re-emits the same wave out of phase. So when the second particle comes along, it doesn't see any wave. So no second particle can enter the state. And you get Fermi-Dirac statistics. In effect, there's an interference between the flux that the particle is following and the one that it re-emits. So there are two that interfere with each other. Current quantum theory can only get that by assuming that the two particles are waves and they form an entangled wave function, and that's what gives you the statistics. But you don't need any of that with this theory. And the statistics only arise as you actually put particles into the states. In the absence of particles, all the different states are completely independent waves. There's no entanglement between them. You only get the effect when particles start being put in them. If this is a boson, the re-emitted wave is in phase, so you get more stimulation, and you get Bose-Einstein statistics. So you don't need any Fock space, any operators. See, I've described how these Feynman diagrams will produce the net flux toward a particle source and how a particle will follow it. I haven't used any operators. See, in standard quantum field theory, you need operators because for a particle to get from A to B, it's a wave in between, so you have to destroy it at A, and then the wave has to carry an operator to recreate it at some point B. But in this theory, the waves go the other way. The particle is always a particle. It's never destroyed. So you don't need any operators. There's no quantization. This is really a completely classical explanation of relativistic quantum scattering. I'm sorry, what? Okay, I'm sorry I didn't get through there. I wanted to talk about the classical limit and a few other nice things, but thank you.